Okay, good morning all of you. Let's get started. I sent you an email about quiz 2 on Saturday, 24. It's going to be from 9 to 5 as you had for quiz 1. And no re-examination. Syllabus will be whatever we covered till 15th of April. Okay? So in yesterday's class, we looked at Lagrange interpolation formula application for deriving the shape function for some of the shape function for or shape functions for some of the quadrilateral elements, 4-node element, 6-node element, 9-node element, like that. So let me quickly summarize that. So this kind of 4-node element, and if you know the nodal coordinates, let's say node 1, node 2, node 3, x1, y1, x2, y2, x3, y3, x4, y4. You can derive the shape functions for this kind of rectangular element. And please note that if the element is quadrilateral, or something else, we are going to map that element onto a regular element. So here shape function expressions are derived. Shape function expression derivation is explained for rectangular elements with 4 nodes at the four corners. And also please note that the node numbering is done in counterclockwise direction. So please keep all those points in mind. And how to derive the shape function for a 2-dimensional element? You need to write the Lagrange interpolation formula for each of the directions separately and take the Cartesian product of that. That is how you get the shape function expressions for n1, n2, n3, n4. And also n1, n2, n3, n4, once you get expressions, you need to also see how the nodes are numbered. You need to also remember how the nodes are numbered. So these expressions are not absolute expressions. It depends on the node numbering. That also I explained to you in yesterday's class. So now how to get the shape function for n1? N1 shape function is going to be it's going to be multiplication of 2 fractions. One of the fraction is going to be x minus x2 divided by x1 minus x2. Another fraction is going to be y minus y4 divided by y1 minus y4. Explain to you how that is obtained. You write the Lagrange interpolation in this direction, x direction. When you want to write the expression for this node n1, shape function for node 1, write the expression, the component in the x direction, multiply with component in the y direction. So that is how you can get all the shape function expressions. So with this kind of understanding, you can easily write the shape function expressions without mugging up all these expressions. Similarly, 6-node element. First of all, this 4-node element is called bilinear element. You can see here, it is written on the top bilinear because it's linear in both x direction as well as y direction. But if you happen to come across a problem, or if you want to capture a response of a quantity which is having higher order variation in one of the direction. So let's say I want to capture the higher order variation. Let's say I want quadratic variation along x direction and linear variation along y direction. Then that is also possible. That results in 6-node element. 3 nodes along x direction. And anyway, this all I explained to you in yesterday's class, taking specific values of x1, y1, x2, y2, x3, y3, x4, y4 expressions for all the shape functions are written, and the same is plotted here. So you can also do that to get a feel for it, to get a feel how the shape functions are varying. And coming back to 6-node element, this is what I'm saying. If you want to have quadratic variation along x direction, linear variation along y direction, you can adopt this kind of 6-node element. Not only for that, 6-node element can be used as a transition element. Transition means some part of the finite element mesh, let's say you have 4-node element, some part of the finite mesh, some part of the finite element mesh you have 8-node element or 9-node element. So you should have a smooth transition between 4-node element region and higher order, like a 8-node element or 9-node element region. In that transition region, you can make use of the 6-node element. So the application of the 6-node element can be a wide variety. Okay. So anyway, this element has quadratic variation in x direction, linear variation in y direction, and see how the nodes are numbered in the counterclockwise direction. And then you need to write how to write the shape function expressions for n1, n2, n3, n4, n5, n6. n1, if you take, you write the Lagrange interpolation formula along x direction, taking these 3 nodes and multiplied with Lagrange interpolation along y direction, taking these 2 nodes. Okay, so if you write that, it's going to be n1 is going to be again multiplication of 2 fractions. One of the fraction is going to be x minus x2 multiplied by x minus x3 divided by x1 minus x2 multiplied by x1 minus x3, and this other part is y minus y6 divided by y1 minus y6. So that is how you can write the shape function expression for n1. Similarly, you can write for n2. n2 shape function expression is going to be it's going to be x minus x1 multiplied by x minus x3 divided by x2 minus x1 multiplied by x2 minus x3. And again multiply this with a fraction y minus y5 divided by y2 minus y5. So that is how you can write it, and after getting these expressions you can plot them here. All that is given for 6-node element. And once you have the finite element shape functions, you can do the linear or interpolation of any field variable and also derivative of that. And taking specific values of the nodal coordinates, these are the expressions that are obtained and these are the plots. Similarly for 9-node element. 9-node element is also Lagrange element. It's going to have quadratic variation along x direction, quadratic variation along y direction, quadratic variation along x direction, quadratic variation along y direction. And the shape function expressions can easily be written by doing the Cartesian or taking Cartesian product of Lagrange interpolation formula written along x direction and written along y direction. So this is how the shape function expressions can be easily written for all the Lagrange elements. And this, you can see here what it is written, biquadratic. It is quadratic in each of the directions, so it's biquadratic element. Okay, and if you want to start with polynomial, instead of using Lagrange interpolation formula, you can select a polynomial having n number of coefficients, because there are 9 number of coefficients, because there are 9 number of nodes. So you need to start with a polynomial having 9 number of coefficients, and then you do all that algebraic manipulation, matrix inversion, find A0, A1 to or A0 to A8, and then substitute back and group the terms having T1, T2, T3, T8, or T9 as common, or you just see how you group the terms having T1 as a separate coefficient, T1 as coefficient separately, like that you do till TA9, and whatever is there, the coefficient, whatever comes as coefficient of T1, that is going to be N1. Similarly, whatever comes as a coefficient for T9 is going to be N9. So that is a cumbersome procedure, and instead of that, you can directly use the Lagrange interpolation formula and write. So these elements, whatever elements we have written the shape functions, for whatever elements we have written the shape functions using Lagrange interpolation formula, they are all Lagrange elements. Okay, we noted first of all 3-node element. 3-node element is a triangular element. So we learned how to derive shape function for triangular element, 3-node triangular element. For a higher order triangular element, there is separate procedure, based on area coordinates. We'll see that after this, maybe in the subsequent classes. So 3-node element is the simplest 2-dimensional element. It's a triangular element. So that's a separate element, 3-node element. After that, 4-node element is a Lagrange element. After that, 5-node element is also there. 5-node element is there. So, but 5-node element we did not discuss because 5-node element is not Lagrange element. 6-node element we discussed, which is Lagrange element. 7-node element is also, you can come up with 7-node element, but that's not going to be Lagrange element. And 8-node element is not going to be Lagrange element. And 9-node element is Lagrange element. So we discussed about 4-node, 6-node, 9-node. And missing elements, 5, 7, 8. Once you understand the procedure for deriving other types of element shape functions, you can easily write those expressions. Okay, so we'll discuss before the end of the class, we'll discuss about that as well. And now coming back to this one once again. So here, let's say 4-node element. For 4-node element, taking the specific values of these coordinates, the expressions for all the shape functions are written, and these shape functions can also be plotted, and that is what is shown here. N1, plot of N1 and plot of N2. You can see here, this is a 3-dimensional plot. This plot is obtained using Mathematica software, and you can see how the shape function N1 is varying. How the shape function N1 is varying. It's varying the value of N1 is going to be here. This is the top view, and this is the 3-dimensional plot. So this coordinate is corresponding to 0, 0. This coordinate is corresponding. This is x-axis. This axis is x-axis. This axis is y-axis, and this actually this z-axis, the axis which is coming out of xy plane, that actually gives you idea about magnitude of this N1. So this is y-axis, this is x-axis, and you can before that you please make a note of this element coordinates. So node 1 corresponds to 0, 0. Node 2 coordinates are 3, 0. Node 3 is 3, 2. Node 4 is 0, 2. So please make a note of it, these coordinates. So whatever plot we are seeing is corresponding to shape function corresponding to node 1. And shape function value of node 1 at node 1 is going to be 1. That is that you already know it. That is same as for 1-dimensional element. And shape function value of node 1 at other nodes is going to be 0. So shape function value N1 is going to be 1 here, and it's going to be 0 at 2, 3, and 4. So it's going to be having a smooth variation. It's going to have a variation, smooth variation from 1 here to 0 here, and 1 here to 0 here. So it's going to be shape function value along this edge connecting 4 and 3 nodes. Along this edge, shape function value is going to be 0, and along this edge is also shape function value is going to be 0. Shape function value of node 1 is going to be 0. So that is what I was telling you when we were discussing about the 3-node triangular element. Please note that this node 1 is not part of this edge 4, 3 and 3, 2. Node 1 is not part of this edge and this edge. So node N1 is going to be 0 along this edge and along this edge. Similarly, N2 is going to be, N2 is not part of this edge 1, 4 and 4, 3. So N2 is going to be 0 along this edge and along this edge. When I say it is 0 along this edge, it's going to be 0 at every point along this edge. 0 at every point along this edge. And what about this edge? 1, 2 and 2, 3. Node 2 is part of that edge. So it's not going to be 0. It's going to have some value with N2 being equal to 1 at node 2. N2 value at node 2 is going to be 1. And it's going to have a smooth variation over this edge, and it's going to be 0 at node 3. So there are 2 points. Shape function of any node is going to be 0 at all other nodes. And shape function value of any node is going to be 0 along the edges over which it is not part of that edge. Shape function value of a particular node is going to be 0 along the edges over which it's not part of that. Okay, so these are the 2 points you need to keep in mind. And then this plots, why it is plotted here, to check whether that whatever just now, whatever 2 points that I mentioned, it is valid or not. You can see here how N1 is varying. This is corresponding to node 1. This is corresponding to node 2, node 3 and node 4. So this is 1, 2, 3, 4. So shape function value is going to be 1 at node 1, and it's going to be 0 at node 2. It's going to be 0 at node 3. It's going to be 0 at node 4. And it's going to be 0 along the edge connecting 2 and 3. And it's going to be 0 along the edge connecting 4 and 3. So similarly here, N2. Okay? And you can plot N3 and N4. Similarly. And you can see here, this is having linear variation along this direction, linear variation along this direction. That's why it's bilinear element. Similarly, if you take 6-node element, 6-node element is going to have quadratic variation along x direction, linear variation along y direction. And that if you plot taking specific values of the nodal coordinates, few of the shape functions. Here the plot is given for N1 and N2. What is the idea of giving for N1 and N2? N1 is the node 1 is the corner node and node 2 is the middle node. So that is the reason it is plotted, N1 and N2. Shape function corresponding to node 1, shape function corresponding to node 2. And you can see here plot N1. This is node 1. You can see here this is 0, 0. And here x-axis is along this axis, along this direction, and y-axis is along this direction. So this corresponds to node 1 and node 2 somewhere here, node 3, node 4, sorry, node 4 here at this corner, node 5, node 6. So you need to make a few of the observations. First of all, whether the shape function value of node 1 is equal to 1 at node 1 or not. That is, it is 1, and it should be equal to 0 at all other nodes. It should be equal to 0 at all other. You can see a shape function value at here. Even though it is here, then 2 is shown here. If you plot it, you will see the exact location. It's going to be here somewhere where it is 0. Where it is 0. Okay. So you need to plot this in Mathematica. Already some of the students are using this MATLAB and Mathematica software. So I suggest you plot it and have a feel for it. So N1 is going to be 0 at node 2, and it's going to be 0 at node 3, 4, 5, 6. So that is one point. Other point is the variation of shape function N1 along x direction. Along x direction it should be quadratic, and variation of shape function along y direction should be linear. You can see here it's quadratic in x direction, linear in y direction. So that is what is shown in the plot. Okay. And what about N2? Here, shape function value of N2 is equal to 1 at location of node 2, and it's going to be 0 along other locations. As I told, this plot, even though it is appearing here in this manner, you plot it and see, because in MATLAB you can actually move your cursor or move your mouse, okay, and then you can see the different orientation and you can have a feel for it. So N2 is going to be 1 at node 2, and it's going to be 0 along other nodes, and it's going to be 0 at other nodes. And also N2, you can see your expression, N2 is quadratic in x and linear in y. So that's why you have quadratic shape in x direction, and it's going to be linear in y direction. Okay, so this is how you can actually have a feel for the shape functions. And also whatever shape functions that you develop, they should not violate these properties. So any questions here? So 4 node element, 6 node element, and similarly 9 node element. Some example is taken here, and also here some plots are also shown. You can also make these kind of plots. Okay. So we studied 4 node rectangular element, 6 node, 9 node. Whatever is missing is 5 node, 7 node, 8 node. And I'm going to explain to you the procedure for 8 node element. And if you follow similar lines, you can derive for 5 node and 7 node elements. Okay. And now, what is the use of these 5 node, 7 node elements or 6 node elements? They can be used as a transition elements between two types of discretization of finite element mesh. Because depending on if you are solving a large problem, it's not necessary. Suppose I am not interested in some portion of that particular structural component. I am not very much keen on getting accurate values, but at particular locations I want to have more accurate values. So in that case, I can use lower order elements in some location, higher order elements in some other location. And in which I should have, even though I'm using 2 different types of elements, I should have a smooth transition. So that for smooth transition, some of these elements can be used as transition elements. So now coming back to this one. So let's look closely at 9 node element, because a 8 node element is a modification of 9 node element. Please see here, 9 node element, you have all the nodes based on the numbering that is given here. Nodes 1 to 8, they're all on the edges. and the node 9 is inside interior, inside the element. It's not connected with any of the edges. It's not connected with any of the edges. Okay, and so you cannot apply directly any boundary condition on node 9. You cannot apply any boundary condition on node 9 because it's not part of the boundary. So node 9 is floating inside without connection to the boundaries. So this kind of element, even though it looks fine, biquadratic, but having this kind of floating node, I can refer to this 9th node as floating node. Having this kind of floating node inside, it may be inconvenient. It may create some problems. So I want to eliminate this 9th node. I don't want this 9th node because it's not going to serve any purpose. It's just inside the element, and only advantage is by having this 9th node, I can easily write the element shape function for all the nodes using Lagrange interpolation, which is very simple formula. So to make use of Lagrange interpolation for an element which is quadratic in both x and y direction, I can take advantage of this 9th node. Other than that, there is no really benefit of having this floating node in the middle. In addition to that, it's going to cause some unnecessary problems. So I want to eliminate this 9th node. Please note that I cannot just simply remove this node because these shape function expressions depend on the location of 9th node. You may say, okay, you take this 9 node element, write all the expressions for shape function expressions for 9 nodes and remove the 9th node. I cannot do that. Okay, because these expressions are dependent on this, assuming there is a node in the middle, these are the expressions. I cannot simply remove that element, that particular node just like that. So people were actually trying different methods. Suddenly, they found surprisingly 8 node element, which is the best solution that is possible, removing this floating node. So that's why that 8 node element is called serendipity element. That 8 node element is called serendipity element, and also 5 node element and 7 node element. Once you understand the procedure for deriving the shape function for 8 node element, you apply same concepts for 5 node element, 7 node element. So then they are also serendipity elements. 5 node, 7 node elements are also serendipity elements. 4, 6, 9 node elements are Lagrange elements. 5, 7, 8 node elements are serendipity elements, rectangular elements. Serendipity rectangular elements. Okay, so now, how to remove this 9th node? I want only the nodes on the edges, 8 nodes. How to remove that? So let's understand the procedure for that. Okay, so you can go through all this, self-explanatory. These are all this stuff which is shown here, example and a plot of it. Okay, so let's read this. Serendipity shape functions for rectangular elements. The following shape functions for rectangular elements have been developed intuitively, hence the name serendipity, based on basic characteristics of the shape functions. That shape function value ni should be equal to 1 at node I and 0 at other nodes. So that is that whatever procedure you use, whatever technique you adopt to get the shape functions, this property has to satisfy. Shape functions have to satisfy this property. Elements based on these shape functions are very popular, means serendipity shape functions. Their main advantage is that all the nodes are placed on element edges and thus there is no interior node. Okay. So one more thing before we proceed. Just now I told you cannot simply remove this ninth node after writing the expressions for all the nodes, because what is going to happen? One of the important properties, sum of all shape functions should be equal to 1. So if you use these expressions, simply remove the ninth node, sum of all shape functions at this location, sum of all remaining shape functions, sum of all remaining 8 node shape functions at this location is going to be 0. And just now you remove ninth node, so there is no ninth node. So sum of all shape functions is going to be 0 here, which violates the requirement that sum of all shape functions should be equal to 1. So that is the reason you cannot just simply forcefully remove this ninth node. Okay? So we'll understand some technique to come up with the 8 node element which avoids this middle node, interior node. So let's to do that, I want you to take a note of this figure. Please take it seriously, okay? When I say you take a note of it, take it. And also here, the rectangular element is shown. And you can see the node numbering. 1, 2, 3, 4, 5, 6, 7, 8. 1, 3, 5, and 7 are corner nodes. 2, 4, 6, 8 are middle nodes, mid-side nodes. Okay, they are the middle of that particular edge side. And this is a rectangular element. You can see here how the coordinate system is defined. This is x-axis, this is y-axis, and here this element another dimension is b. So please take a note of this element. And this rectangular element, this the element is rectangular element, but I want to I want to do some mapping, okay, onto a square domain. This is x-axis, y-axis. X-axis is going to be mapped onto s-axis. Y-axis is going to be mapped onto t-axis. And what is the relationship between s and x, y and t? T and y, they are given here. So this rectangular element is going to be mapped onto a square element where s goes from -1 to 1, t goes from -1 to 1. So in the s coordinates, s and t coordinate system, in s and t coordinate system, instead of x and y, after mapping, using this kind of mapping, s is equal to 2x divided by a, t is equal to 2y divided by b. So this rectangular element gets transformed into a square element, where s-axis, s goes from -1 to 1, t goes from -1 to 1, and the corner nodes coordinates in s and t axis are these, whatever is written here in red color: -1, 1, 1, -1, 1, 1, -1, 1. And once I have written coordinates of only the corner nodes, what about the middle nodes? You can easily guess. This is going to be 0, -1. This is going to be 1, 0. This is going to be 0, 1. This is going to be -1, 0. So that, because I don't want to load this figure with too much information, that is avoided. Okay. So please take a note of this. Please take a note of this figure. So these expressions for N1 to N8, N1 to N8, only 8 nodes are there. N1 to N8, they are written in S and T coordinate system instead of X and Y coordinate system. And if you want to transform these expressions into X and Y coordinate system, you just use this mapping, and then you can express these N1 to N8 in X in terms of X and Y. Okay, so this rectangular element, which is having dimensions A by B, is mapped onto a square element of 1 unit in each direction. Sorry, 2 units in each direction. 2 units in each direction, with a s-axis going from -1 to 1, t-axis going from -1 to 1. I hope you have taken note, whatever based on my suggestion, you have taken note of all the information in this figure. Now, I'm going to explain you important concept, how to write the shape functions for this kind of 8-node element. So now let's focus on node 1. I'm showing it where this pointer is located, node 1. What is the property of this? What property this expression for node 1 should satisfy? N1 should be equal to 1 when, please note that now we are talking in terms of S and T coordinate system. N1 should be equal to 1, whatever expression for N1 we write, or whatever expression for N1 we arrive, N1 should be equal to 1 when I substitute S is equal to -1, T is equal to -1. And it should be equal to 0 if I substitute the coordinates of other nodes, 2, 3, 4, 5, 6, 7, 8. It should be equal to 0 when I substitute the coordinates of other nodes. I hope you agree with that. So that is the condition it has to satisfy. So now, if that is the condition N1 has to satisfy, we need to carefully, yesterday I was telling you, when we are solving, or when I was explaining for solving 2-dimensional problems using classical methods, how to intelligently guess admissible trial solution. You recall that whatever I explained, same thing we are going to use here. So N1 should be equal to 1 at the location where I am showing this pointer, and it should be equal to 0 at 2, 3, 4, 5, 6, 7, 8. Okay, I need to do it carefully. And what is the equation of this line? What is the equation of line connecting 3, 4, 5? What is the equation of line connecting 3, 4, 5? It is nothing but S is equal to 1. S is equal to 1 is the equation of this line. You can see here S is equal to 1, S is equal to 1. So S is equal to 1 at any point along this line. S is equal to 1 is the equation of that line. Or it can be also written as S minus 1 is equal to 0. Equation of this line is S minus 1 is equal to 0. You please make a note of it. Equation of this line is S minus 1 is equal to 0. So in the expression for N1, I should have S minus 1. And N1 should be equal to 0 along this edge, connecting 7, 6, 5 nodes. And what is the equation of this edge? T is equal to 1, or T minus 1 is equal to 0. So expression for n1 should consist of the term t minus 1. So n1 expression should consist of s minus 1 and also t minus 1. So by including these two terms, I am going to straight away eliminate. I am going to straight away satisfy the condition that n1 is equal to 0 along this edge, n1 is equal to 0 along this edge. I am going to straight away satisfy the condition n1 is equal to 0 at node 3, 4, 5, 6, 7. And what are the other two nodes that are left out? 2 and 8 are left out. So I want to include line connecting nodes 2 and 8. Line connecting nodes 2 and 8. What is the equation of line connecting 2 and 8? You need to go back to your high school mathematics, okay? If you are given 2 points in space or in two-dimensional space, how to come up with the equation of a straight line joining those 2 points? So what is the equation of line connecting 2 and 8, nodes 2 and 8? First of all, what are the coordinates of node 2? Coordinates of node 2 is s is equal to 0, t is equal to minus 1. Please take a note of it. Coordinate of node 2 is s is equal to 0, minus 1 are the coordinates of node 2. And what about coordinates of node 8? Coordinates of node 8, 0, minus 1. 0, minus 1 are the coordinates of node 8. And this red dotted line is line connecting node 2 and 8. Okay? Here node 2 is coordinate is 0, minus 1, and node 8 coordinate is minus 1, 0. So equation of this line is s plus t is equal to minus 1. Equation of that line is equation of line connecting 2 and 8. Nodes 2 and 8 is s plus t is equal to minus 1. Or in other words, equation of that line is s plus t plus 1 is equal to 0. So I need to include this term also in node 1. So if I include this term also in node 1, I can eliminate or I can satisfy the condition that n1 is going to be 0 at node 2 and 8. So now with this, I don't have any other nodes. Okay, there are only 8 nodes, so I satisfied all that. So node 1 expression should contain s minus 1, t minus 1, s plus t plus 1 is or s plus t plus 1. So that is what is written here. Node 1 expression should consist of s minus 1, t minus 1, s plus t plus 1. So these are the things that needs to be there in shape function expression for node 1. Okay? And now a general form of that, let me write it here. Let me quickly write here. N1 is equal to s minus 1, t minus 1, s plus t plus 1. Okay? So these terms should be there. Or some constant should be there. Okay? some constant should be there. So this is subscript here. Is that? Anyway, I'm unable to see that. Where is it? Font subscript. Okay, so this is a general expression for N1. And what is the other condition N1 has to satisfy? N1 evaluated at -1, S is equal to -1, T is equal to -1 should be equal to 1. Now you substitute S is equal to -1, T is equal to -1 and impose this condition, and it turns out that A naught is equal to -1/4. So now if that is the case, then I can easily write N1 is equal to Is this clear? How the expression for N1 is derived? How the expression for N1 is derived? So please take a note of this. Whatever I have written here, please take a note of it. It may not appear on the slides which are posted on the Moodle. Okay, I'm sometimes I'm intentionally doing because I want to draw your attention when I was explaining. Okay, so please take a note of it. What I will do is I will quickly write the procedure. This is corner node. N1 is corner node. Okay, I'm going to explain to you for middle node. Let's say N2 quickly. Let me change the coefficient here. Let's say A1. Sorry, here it should be. So please say N2. N2 is the middle node here, mid-side node. N2 should be equal to 0 at the locations 3, 4, 5, 6, 7, 8, and 1. And for N2, it's very straightforward. I should include equation of this line connecting 3 and 5. I should include equation of this line connecting 5 and 7. I should include equation of this line connecting 7 and 1. What is the equation of line connecting 3 and 5? S minus 1 is equal to 0. And equation of line connecting 7 and 5 is T minus 1 is equal to 0. And equation of line connecting 7 and 1 is S plus 1 is equal to 0. Or S is equal to minus 1. So it should consist of terms S minus 1, T minus 1, S plus 1. And in addition, some coefficient, because it has to satisfy, N2 has to satisfy the condition that N2 evaluated at this node 2 should be equal to 1. It has to satisfy. So to determine that, I am including this coefficient A1. So impose that condition, and it turns out that A1 is equal to half. Substitute that, you get S minus 1 multiplied by T minus 1 multiplied by S plus 1 divided by 2. Okay? So S minus 1, S plus 1. It's S square minus 1. S square minus 1. Instead of writing S square minus 1, I want to write it as 1 minus S square. If I want to write 1 minus S square, minus is going to be there. That minus, if you multiply with this, it's going to be 1 minus T. So the expression for N2 is going to be 1 minus S square multiplied by 1 minus T divided by 2. So that is what is written. So this procedure gives you explanation for corner node and middle node. Same procedure you apply for the other nodes, you can easily derive. Okay? Any questions here? So this is how you can derive the shape function for 8 node element. Okay? So let's say I have a 5 node element. I have a 5 node element. Please note that for a rectangular element, node should be there at, one node should be there at each of the corners. So let's say I have a node at this corner. 5 node element I am explaining. Or before 5 node element. Before 5 node element, let's discuss about 7 node element. Let's say this 8th node is not there. I have only 7 nodes. 1, 2, 3, 4, 5, 6, 7. So how do I derive the shape function for 7 node element? If I take node 1, okay, node 1 should be equal to 0 along these edges, connecting 3 and 5, 5 and 7. So it should consist, for 7 node elements, I am explaining procedure for 7 node element. Assuming there is no node 8. Okay. So if I include this term, the equation of this line, which is S is equal to 1 or S minus 1 is equal to 0, T minus 1 is equal to 0, it's going to be 0 along this edge, along this edge. And there is no node 8 here. There is no node 8. How do I eliminate node 2? I'm going to include this line. I'm going to include this line. Line connecting node 2 and 4. Include equation of that node, that line. And then follow the similar procedure. Multiply with the coefficient, determine the coefficient based on the condition that N1 evaluated at node 1 is equal to 1. You get that whatever coefficient value. Then you plug in that. Okay? Similarly, if you want to derive for 7-node element, this kind of node numbering 1, 2, 3, 4, 5, 6, 7. There is no node 8. For this node, I want to write shape function for this node. 2. Node 2 shape function. Node 2 shape function should be 0 along this edge, and also along this edge. Okay. So you get almost same shape function expression. So like that you can derive the shape function expression. And please note that this is one of the procedure. If you have a better idea, then you can try that. But whatever expressions for shape function that you get, they have to satisfy what are called consistency conditions. First of all, shape function value of ith node evaluated at I should be equal to 1, and it should be 0 at any other node other than I. That is what is called Kronecker delta property. And also sum of all shape functions evaluated at any point in the domain should be equal to 1. And also derivatives, sum of derivatives of shape function should be equal to 0. When I say derivative, whether you take derivative with respect to x or with derivative with respect to y for 2-dimensional case, or derivative with respect to z for 3-dimensional case, it should be equal to 0. Or derivative with respect to s, sum of all derivatives of shape function with respect to s should be equal to 0. Sum of all derivatives of shape function taken with respect to t is equal to 0. Or in 3-dimensional case, you may have one more thing, RST coordinate system. The same thing is applicable there. So this is all about serendipity elements. Okay, I'm going to stop in a minute. And with this explanation, you can easily tabulate the shape function expressions for different types of elements. Node 4 to node 9. They're all given. Whatever explanation that I gave you, 5, 7, 8 noded elements can be used as transition elements. That explanation is given here. You can go through it, or we'll go once again in the next class. Okay. So let's meet on Saturday for quiz. Syllabus taught till last Thursday, that is 15th April, it will be there. Okay. And if you have think about whatever we covered in today's class, if you have any questions, we'll discuss in the next class. Let me take attendance.
Sir, one question.
Yeah, tell me.
Sir, is it necessary that nodes other than corner nodes should be in the middle?
What is that?
Sir, other than corner nodes, the nodes should be in the middle, exactly in the middle. Is it necessary that?
No, it's not. It's not the middle. No? If you take 6-node element that is shown, that is illustrated example 6-node element, the middle node is not exactly at the middle. They need not be equally spaced. Okay. But please note that whatever element, the actual element, whatever may be the case, when we map onto a parent element, which is an S and T coordinate system, our nodes are going to be equally spaced. Similar to the 3-node, one-dimensional 3-node element that we looked at. Okay. If you recall one-dimensional 3-node element, x1, x2, x3. The locations need not be equally spaced, but we are going to map that element onto S going from -1 to 1 with middle node at S is equal to 0. So whatever 8-node element shape function that I derived is for parent element in S and T coordinate system.
Okay, sir.
Okay. Yeah. Think about it. Maybe you may get more questions or more doubts. Think about it. Okay. We'll discuss later. Okay. Thank you.